Hi guys, this is Savin Vishwanathan. So I was thinking about leaving a video on how to model the ship's hull using the XT curve method and how to calculate its GZ curve. So in this presentation, I'll be telling you how to model the ship using XT curves, how to define the surfaces, how to define the solid hull of the ship with a bow thruster, and how to subdivide the hull into different compartments, and how to carry out the stability check for different loading conditions and determine the GZ curve. So we'll start with what will be given to you. So you'll be given a question paper that looks something like this. The question paper will have all the points of the XT curves defined, of the longitudinal center line, the deck line, the transom, and the sections. It'll also give the boundaries of the various compartments and as well as the dividing surfaces. It'll also give you the light ship weight, the centroid, the permeability of different tanks, and the loading condition will be given to you in a separate sheet once you finish modeling your surface and subdividing the hull. You can contact the invigilator and then he'll hand over the loading condition to you. And from that loading condition, we'll have to calculate the GZ curve. So to begin with, we will open a new Paramarine window. And the first thing that you need to do is define the XT curves that define the surface of the ship. So you'll have to add a geometric placeholder and rename that as XT curves. And inside the geometric placeholder, you will have basically the longitudinal center line, the deck line, the transom, and the section curves. So I'll first insert an object from the hull generation folder that's called the XT curve, and now I'll rename that to the longitudinal center line. Right, now this longitudinal center line curve lies in the y plane as I've explained in class, and all the curves that, rather all the surfaces that meet this curve is tangent in the y direction. Basics I'm not explaining again because that has already been covered in class. So now I'll just display the grid to make my modeling easier. So I'll just check the location, so it has to be at 0 meter, and then I will set the location of this to 0 meter, and even for this I'll set it to 0 meter to start with. Then I will display the XZ grid, which is the y plane. So that shows the y plane, and I'll switch on the UCS. So this shows the X direction, Y, and the Z directions. I'll just revert to the normal orthogonal view, and this line actually shows the 0 of the coordinate system, and each major grid line is 10 meters. So from the question paper, you can get the coordinates of the center line. So from that, I'll be basically modeling the longitudinal center line. So the longitudinal center line in this case is defined by 11 points. So the first point is given as 50, 0, 10. So I'll go to the XT curve again, and From operations, I will go to insert point, or you can alternatively use this graphics user interface here. So I'll use that, and it's at 50, 0, 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So 1, 2, 3, 4, 5. Yeah. So it'll be this point, somewhere this point. And point 2 is 4700. So it'll be somewhere here, let's say. And point 3 is 4500. Let's say it's somewhere here. And point 6 is 802. So let's say this is 80. Oh, before that, point 4 is 1200. So that's 1200. You have, maybe I'll just switch off the thing. That makes it easier. So we did point 4. Point 5 is 1000. Point 6 is 802. Right. Point 7 is 604. Approximately place the points. Point 8 is 505. 505. Point 9 is 305. Point 10 is 005. And point 11 is 0010. So just approximately place the points and press escape to come out of that. Now some points are to be defined properly. So the first point is 50, 0, 10. So just sorry about that. Just define that as 50. Okay. Point 2 is 4700. So that's 47. And you have 0 and you have again 0. Point 3 is 4500. 45, 0, and this becomes a 0. Right. Point 4 is 1200. Do that again. 12, 0, and this is 0. Point 5 is 1000. It's a 10. And this becomes 0. Point 6 is 802. So it's a 2. Point 7 is 604. So that's a 6. And that's a 4. Point 8 is 505. So that's 5, 0, and oh, I'm sorry. This is 5, 0, and this is 5 again. Point 9 is 305. So that's 3, 0, and a 5. Point 10 is 005. So 00, and that becomes a 5. And point 11 is 0010. So that's a 0. This is 0, and that's a 10. So that gives the approximate shape of the center line. Now we'll have to Define few points which are knuckle points that are already given in the question paper. So point 3, point 4, point 6, point 7, point 9 and point 10 are knuckle points. So pick up point 3 and in the operations set it to a knuckle point. Right? Pick up point 4 and set it to a knuckle point. Point 5 is not knuckle, point 6 is knuckle, so pick up point 6 and set it as a knuckle point. Point 7 is again a knuckle, so take that up and set it to a knuckle point. Point 8 is not knuckle, point 9 is a knuckle point, so set that to a knuckle point. And point 10 is also a knuckle point, so set that to a knuckle point. Right, so that defines the longitudinal center line of your ship. Now we'll go into the modeling of the deck line. Again, the coordinates of the deck line are given in the question paper. So we'll have to again insert a new XT curve from the hull generation folder and rename that to deck line. Right, now this deck line, as you all know, lies in the zip plane and there is no tangency defined for the deck line. So again, I'll start by inserting points. Before that, let me just switch off this grid. Right, so this is the longitudinal center line that I've defined. Now we'll have to define the deck line, and the first point of the deck line will be locked to the first point of the longitudinal center line, and the last point will be locked to the last point of the longitudinal center line. So I'll go to insert points and pick up, and I'll pick the snapping lock. So that'll snap to that point. It will be easier for me to model if I go to the plan view. So modeling on the port side. So the second point is 46.207, 5.679, 10. So I'll just place it somewhere there approximately. Point 3 is 46, 5.70, 10. That's somewhere near that. Point 4 is 40, 10, 10. So that's somewhere here. Point 5 is 31, 10, 10. Right, point 6 is 0, 10, 10. And point 7 is the copy of the last point of the longitudinal center line. For now it will show as a beat point, but that's okay, we can change that later. So just select that, and oops, I made a mistake in doing the line, so I'll just go to edit and go to undo, and then I'll have to append a point to this. So I'll just select the decline, select append point, and then I'll lock to that point. So that's done. Now we'll have to set a few points as knuckle points. Those points are given in the question paper. So just control and you can pan that. Right, so point 2 is defined by 46.207, 46.207, 5.70 is a distance anyway. So point 3 is 46.5, 0.3 is 46. 5.70. 0.4 is 40, 10, 10. So that's 40. That becomes a 10. That's already a 10. So 0.5 is 31, 10, 10. So that's 31. That becomes a 10. 0.6 is 0, 10, 10. So that's 0, 10, and 10. And 0.7 is anyway logged on to the last point of the longitudinal center line. So we can change that bead to a copy of. So select copy of from here, and that is the 11th copy of the 11th point of the longitudinal center line. So I'll pick up that from the list. You can also pick up from the drawing if you want, but this is more accurate. So now that becomes a copy. You see the small rectangle there, that becomes a copy point. Right, now we have to set few points to knuckle. So 0.5 is a knuckle, 0.6 is a knuckle. So let's say 0.5 is set to knuckle and 0.6 is set to knuckle. So that pretty much defines the decline of the vessel. So I'll just minimize all the unwanted things. Now we have to define the transom, which runs from this point of the duct line to this point of the longitudinal center line. So I'll have to insert an XT curve object. Again, I'll go to hull generation and insert an XT curve, change that to transom. Okay, now in transom, I'll have to again insert points. The log option is already open, so I'll select this point first, I'll select this point next, and the second point I'll place it approximately somewhere here. Exit that and open this, and only point 2 needs to be changed, and the coordinates of point 2 are 0, 10, and 5. So this becomes 10. Okay, and this becomes 5. So you've defined the transom. Again, you can change that to lie on the X-plane, because that is a curve defined on the X-plane, and it doesn't have any tangency definitions. So tangency you can leave it as not defined, but the location you have changed to X-plane. Now I have a section at 25. So for that, again, I'll insert an XT curve from hull generation, take an XT curve, and the location of this is, again, since it's a section, it's on the X-plane. No tangency defined. So the pointer, you can take the log option, and then this shows a bead. So approximately at 25, place that, and come to this view to place the second point. So that's now 0.1, 0.2, and 0.3. So that's 0.1, that's 0.2, and that's 0.3. So 0.1 is at 25, 10, 10, and 0.3 is automatically adjusted to that because it's a bead. 0.2 is defined as 25, 9.317, 9.317, and Z as 3.074. Right. So now we have defined the section. So all we need to do now is to define the deck center line and then start making the surfaces. So again in the XT curve I'll insert another object from our generation. So that's called the deck center line. And this deck center line lies in the Z plane. So that lies in the Z plane, right? And the points are to be locked on to the first and last points of the longitudinal center line. So I've chosen the snapping lock and I'll just lock it like that. Now you see that the curve that you wanted uh, to be a straight line, the curve that which you wanted to be a straight line is now shown as a curve. That's because you've defined a tangency for the longitudinal center line in the y direction. So whatever you do, that curve is going to bend and be tangent in the y direction. So to remove that, all we have to do is remove the tangency condition at this point. So we'll select that point 1 and go to operations and do our right tangent. Similarly to point 2, go to operations and our right tangent. So now that becomes a straight line. Now we need to define a section for the deck. So we'll again insert an XT curve from our generation, and that'll be called the deck section, let's say. So this deck section should be between the deck center line and the deck line. I'll go for an insert point and I'll select any 2 points, and those points are anyway uh, it's going to be straight. The line is going to be straight. So I'll just, for better presentation, I'll just set it to x equal to 25, and you can actually set the location to explain, and then both points will be automatically adjusted. So that's that. So now we have finished the modeling of the XT curves. You can use these XT curves to now define the surface. So for that we will insert another geometric placeholder called the hull surfaces. Right? So under the hull surface I'll again insert another geometric placeholder and call it the hull port. Let's say hull surface port. Right, under that I'll insert XT surface. Right, I'll rename that to again port surface. The name really doesn't matter, so it's just for your identification, so give it a logical name. Um, the type of the surface is a Kuhn's linear Bezier that I want. I'll set that. Now the boundary curves for the port hull side are the deck line, the longitudinal center line, the transom, and the section. So I'll just copy those curves, the longitudinal center line, deck line, to the boundary curve. Copy that and I'll paste that in the boundary curve. Paste it as a pointer. Now the internal curves are the transom and the section at 25. Longitudinal center line, deck line, transom. Oh yeah, this is my section curve. So I'll just rename that to section 25 for ease of identification. So now I can copy transom and section 25 to null curve. Right, and that defines the port surface. That's actually the port surface. Yeah. So you have to look at it like this. Now that becomes the port surface. Now I'll have to define the port deck. So I'll again insert an XT surface and rename that as port deck. And again, the boundary curves in this case are the deck line and the longitudinal center line. Sorry, the deck line and the deck center line. So I'll just copy those deck line and deck center line. Sorry, deck line and deck center line to the boundary curves. And the deck section I'll be copying into the internal curves. And again, the type of surface that I need is a Coons linear Bezier. So now you have the port side hull as well as the port side deck. These are in two separate patches. You'll have to join them. So for that, I'll use something called a patch surface, which is again it comes under solid modeling. So that's called a patch sheet. Produce a sheet by sewing patches together. So I'll select that, rename that to port hull complete, port hull and deck, whatever. So now all I need to do is copy the patches that I want to sew together. So I'll just copy that and I'll paste it there, and I get a result which is the sewn patch of the port side hull surface as well as the port side deck surface. So that's that. Now I need to make the starboard side deck and hull surface. For that, all I need to do is scale the port side deck and hull surface. So for scaling that, we have to first copy this result and paste it inside this. Paste as a copy of, right? Rename that to starboard hull and deck, right? And do a scaling operation on this. So just go to operations and go to scale coordinates. So the only coordinate that you're going to scale is the y coordinate. That's -1. Right. So you get that. Now we have to join these two patches together to form a enclosed volume. So for that, what we do is we again insert a patch surface. So let me see, again the hull surface I'll insert from solid modeling. So a patch solid. So I can basically join these two patches and define it as a solid. So I'll use that option and just specify the patches that will make up the solid. So one is the um, result of the port hull and deck. So I'll copy that and paste it here. Paste special as a pointer. Okay. and the other is the starboard hull and deck. So I'll just copy that and paste special as a pointer again. So now you have your hull surface, which binds the volume of the hull, and it is modeled as a solid. Now what we have to do is we have to define the bow thruster tunnel. So to define the bow thruster tunnel again, I'll have to define a cylinder that defines the bow thruster tunnel and subtract that cylinder from the solid hull. So for that, I'll again maybe insert another another geometric placeholder. Sorry for that. You have to come out and then insert a placeholder. So that will be the hull with BT. Let's say hull with BT, right? And in this hull with BT, you have to basically copy this patch solid, the result of this patch solid, and paste special as a copy of, right? You can rename that to hull solid or hull with BT. Now to define the bow thruster, we need to define 2 points, and then from the 2 points you can define a radius and form a cylinder. For that again I'll insert a geometric placeholder, rename that to BT data, right? So in that I'll have to define 2 points. So again I'll go to geometric definitions, point. So I'll change that to BT point port, right? And the coordinates are given in the question paper. That is given as the axis of the bow thruster tunnel lies at x equal to 45 and this is equal to 2 with a radius of 1 meter. So x equal to 45, right? Is it equals to 2, right? That's port point. So you can just copy that and paste that and make that as BT point starboard. Just remember to change the coordinate of x, I mean not x, coordinate of y to -10. So we forgot to keep that as, so at the port you will give y as 10 and at the starboard side you will give y as -10, and so you have these 2 points that define the end of the bow thruster tunnel. Right, now in the bow thruster tunnel I'll insert a solid body. So insert a solid body. It shows as not valid. So I'll just click on that, go to operations and go to cylinder from extent, or you can just go to cylinder and the point 1 you can select that point as the bow thruster point port, and point 2 you can select that as the bow thruster point starboard, and the radius is 1 meter. So you define that and you define a tunnel that you define a cylinder that defines the bow thruster tunnel. Now all you have to do is go to this hull with BT, right click go there, select subdivide, oh sorry, not subdivide, select, go there, select subtract, and for the tool you will use the both are a solid body. So just go there, and this is the one. Hull with BT data solid body. You can just select that, right? Okay. So now you have the solid hull with the both at top. Now you'll have to subdivide this hull to define the different compartments. So for that, again, you will insert a geometric placeholder. Is it still recording? Yeah. Okay. So you will insert a geometric placeholder. Where I go? Okay. So here, rename that to subdivided hull. Right, now for the subdivisions, you need to define the planes first. So inside this, I'll again add a geometric placeholder, rename that to division planes. So my division planes are defined by x equal to 43, 28, 15, 5, y equal to 7 and minus 7. So let's see, I'll insert um, a plane body. So right, so this is x 45, so 43, x 43. Okay, so I'll just go to this and go to operations and plane orthogonal. And so this is the plane that is orthogonal to the x plane. So distance from the origin is 43, right? So if you want to see that, so this is your plane. That's approximately where you want, not approximately, that is exactly where you want your um, forward collision bulkhead. So that be there. So I'll need how many X planes? 1, 2, 3, 4 X planes. So I'll just copy that and keep pasting. 1, 2, 3, 4. So I just need yeah, I need 4 in total. So the next is X28. So I'll just set this distance to 28. Okay. Next is X15. So I'll just set the distance to 15. Next is X5. So just rename that X5. 5. Right, so you have all the X planes that subdivide the ship. Now you need to define the Y planes, and that is given by, so just copy that and paste it again and go to plane orthogonal and just change the selection to Y, and the port side plane, port side Y plane lies at a distance of 7 meters from the center line or the center plane, so keep that as 7 and just rename this as port 7, right? So and then again copy that and paste that and rename that to starboard 7 and make sure to change the coordinate to minus 7, right? So these are the planes that are going to subdivide your ship, right? So now I'll just copy the hull with VT and paste that here as a copy of, right? And now I'm going to so I'll just rename that to subdivided hull, right? Okay, now I'll start dividing this. So go to operations and go to subdivide. It'll ask me to select the division bound. My first division bound is x equals to 43. So now I have two solids. right? So is that, yeah. So this is my for pig tank. So I'll rename that to for pig tank. Okay, the for pig tank flooded permeability is given as 95 and tank permeability is given as 93. We'll set that. And now the other body, I'll again subdivide that with the division bound x equal to 28. Right, so now I have two bodies. Now this body I have to again subdivide into the cargo tank and into the wing ballast tanks. So I'll take this body and go to operations, subdivide with the outside plane, right? So that is my ballast tank, water ballast tank port 1. So this body again I'll have to subdivide with the starboard side plane. Okay, so that is my water ballast tank starboard 1, right? And this becomes my cargo tank 1. Okay. Similarly, this body will again have to be subdivided by the explain. So operations subdivide, division bound in this case is x15. So do that. And this body again has to be subdivided to form the ballast tanks. So again go to operations, subdivide, use the port side. So this is the water ballast tank port 2, and here again subdivide this body into the water ballast tank starboard side. So use the starboard side plane and subdivide that to, yeah, so this is the water ballast tank starboard 2, right? So you have this one, which is the cargo tank 2, right? So now the remaining body again has to be subdivided to form the engine room. So that is at x equal to 5. So do that. So that becomes your aft peak tank. So aft peak tank, right? And this is your engine room, which again has fuel oil tanks on its wings. So go to subdivide and select the outside plane and rename that to fuel oil tank port. Right, and again subdivide this body into fuel oil tank starboard. Starboard. Okay. And this is now your engine room. So engine room. We have set the permeabilities of all these. So except for the aft peak and for peak tank, all permeabilities is given as flooded permeability 98% and tank permeability of 95%. So that's done for the last tank port, the last tank starboard 98. sorry, set that to 98, set that to 5. Okay. Set cargo tanks similarly 98, 95. That this is boring. 98, 5. Again, set that to 98, 5. This one. Okay, 98, 95. This one. 98, 95. Oh, that was the half peak tank, so that goes to 95 for the flooded permeability and 90 for the tank permeability. So the fuel oil again has 98 and 95. These are assumed values. The actual flooded and tank permeability will depend on the construction of your tank and for what kind of fluid you're going to use the tank for. So in this case, we'll just stick with 98 and 95. 95, okay. And finally, for the engine room, the flooded permeability can be approximately 65% because machinery takes up a lot of space. Tank permeability again, just for namesake, you have to define that with the percentage. So that's that. So your hull subdivision is over. You have defined your tanks. You have defined the engine room. And now we can go into stability. So we will insert a stability placeholder. Right. So the stability placeholder, the first thing we'll define is the fluid densities. So click on stability placeholder, copy that and paste that again and rename that to densities. So sorry, rename that to densities. Right. And then you can insert a density object from this one. So in this case, we are going to carry fresh water. So this is freshwater density. You can just change that to freshwater. And then we're going to carry fuel oil. So just rename that to marine diesel oil. And the density of marine diesel oil is around 0.85, specific gravity of 0.85. That's 850 kilograms per meter cube. So, and obviously you'll need the density of seawater to define this one. So let's rename that to seawater and change the value to 1.025 ton per meter cube. Right. So let's see. Right. So the densities are defined. That density actually has to be inside this placeholder. So just place it there. Yeah, that's easy. Right, now you'll have to define the stability criteria. So select the stability placeholder, go to basic stability and just select the stability criteria object. Where is my stability criteria? Yeah, stab settings. Right, so let that remain at the default values. You don't have to change anything in that. Now the next thing that you have to define is the hull envelope. So again, select the stability placeholder and go to the hull envelope. Right, now that shows is not valid, so we need to define something. So make enable checking to yes. Right, the tolerance will be that same thing, and for the buoyant body, you are going to use the full subdivided hull as your buoyant body, so a special as a body pointer. Right, so now the color has changed to green, and that means that your hull envelope is almost defined. Right, now the aft perpendicular baseline is at about 3 meters. The forward perpendicular is defined at around, just check the question paper. So forward perpendicular baseline is at 48. So make that a 48, right? The aft marking datum is at x equal to 11, 11, and the forward marking is at x equal to 43, I guess. So make that 43. Right, so now just let's see. Yep, hull envelope is checked, so all data is complete. Now you have to define the lightship weight. So for that, you will insert an object called the basic hull, so or the basic ship. So now you'll have to point to the stability settings that you've already defined. So just point to that, right? Hull envelope you've already defined, so just point to that. No growth, no marine growth is to be considered, and the datum, that is where you define your lightship weight. So your lightship weight is given as 1000 tons, and the centroid is given in the question paper as 2505. So 25, 0 and 5, right? Okay. And the water density, in this case the seawater density, so going to that. And that shows the centroid of the lightship. So that is done. Basic ship is also checked. Now you'll have to define your loading conditions. So for the loading conditions, let's see. Again, inside the stability placeholder, insert a loading condition object. Okay, and point your basic ship to the basic ship that you have defined. And in tanks on, we have to actually copy all these as tanks. Let's copy all that and select the tanks on and go to operations. Sorry, go to base special and paste it as a tank. Now we just have to define what fluid is to be filled in each tank. So for a big tank, it's obviously seawater. So we select that, right? In the water ballast tank, it's again seawater. So starboard again, it is seawater, right? And cargo tank. Let's say we're going to carry fresh water, so I'll just point this to fresh water. In water ballast tank again, it is seawater. Again, water ballast, so it is seawater. Cargo tank 2, fresh water. And then Aspik tank, it's again seawater. You're going to take ballast on that. So your fuel oil tank port, it is marine diesel oil. So deal with that. Fuel oil starboard, it is again here. And in the engine room, just to satisfy the loading condition, you'll just specify the fluid type as seawater, but the filling proportion is anyway 0, so that's fine. And then you'll come down and define the water density to be 1.025. So once you define that, you will get a water line. You can see a water line that has appeared here. So this actually shows the draft of the ship in light ship condition. So it has a slight trim by the aft because the draft in the forward is less than draft aft. So that means the trim is by the aft, which is the ideal case for a light ship condition. Right, so we'll now need to fill in the tanks with whatever data is given to you in the loading condition sheet. So for an example case, let's say the cargo tanks are both filled 50%, so that can be 50, right? And cargo tank 2 is similarly 50. Right, so now just have a look at your ship. Now when the cargo tanks are 50% full, the ship has a trim by the forward because the draft forward is much greater than draft aft. So you'll have to correct that trim. Let's say, so I'll put the aft peak tank. I'll put some water in the aft peak tank. Right, so I'll fill that to around, let's say 70%. Right, so now you're almost, again, you have a trim by the forward. That's okay. You will take some water in the number 1 ballast tanks. So water ballast tank 1, let's say I'll keep 20% there. Now you see, I took water in the starboard side tank, so that has gone down and the port side has come up, so there's a heel on the ship. So I'll have to take some water in the port side tank too. So do that. Basically, all the loading condition, the percentage fillings will be given in the question paper, so you don't have to worry about that. You just have to take that into consideration. So in this case, again, the trim is by forward again. So I'll take some that's okay. Looks okay. Yeah, so maybe I'll just fill up the half-peak tank a bit more. So when you do it, the loading conditions are already given in the paper, so you just need to select the tanks and give the filling percentages, and that'll be enough. Right, so now I have a trim by the aft condition, and for this condition, I'll have to find out the stability. I mean, I'll have to find out the GZ curve. So I'll insert the GZ curve object. So let me see basic stability GZ. Right, so Stability settings, again we'll just point to the stability settings that we started earlier. Loading condition, point to the loading condition, right? No damage case, no wave, heal range. So in this, we can insert the angle values at which you need to make the GZ curves. So I'll just insert from this a variable, so that will be 30 port. Let's say 30 port, right? So that'll be 30 degrees. I'll just copy that, and I need 20 port, I need 10 port, I need upright, I need 10 starboard, I need 20 starboard, I need 30 starboard. Right, so I'll change this now to 20 port, and I'll change the value to 20. I'll rename this to 10 port, and I'll change this value to 10. And this is my upright condition, so upright. So I'll just change the value to 0. Rename this to 10 starboard, and change the value to -10. This is 20 starboard. I'll change the value to -20. And this is 30 starboard. So I'll change the value to -30 and rename that as 30 starboard. Right, so you basically have your loading condition defined. These are the tanks that are defined. So I'll just minimize the tanks, show you the percentage fillings. Right, so that's the for-peak tank, which is empty. This is the water ballast tank, which is partially filled. Is this, yeah. So that is the water ballast tank that is partially filled. Starboard side, this is the cargo tank, 50% filled. Water tank, port side, which is empty. Starboard, which is empty. Cargo tank, which is partially full. Aft-peak tank, which is almost full. Fuel oil tank port and fuel oil tank forward. So I'll just define the values for those two. So let's say I have 20% fuel in that, and I have 20% fuel in this. Right, so these are the tanks that you've defined, and this shows the filling of the tanks. Just highlight that. And for this loading condition, we have calculated the GZ curves, which can be obtained from here. This is the output that you have to give for the stability part. So in your exam, the modeling part, till the definition of the tanks, uh, till the subdivision of the tanks will be 60 marks, and whatever you do after that will be for 40 marks. And that brings us to the close of this video. I hope that you all can make use of this and study well for the exam. You will get uh, almost a similar type of hull, but the only thing that'll change is loading condition. So each person will have a different loading condition. So make sure to know how to model that. Thank you. So that's it.